All right, let's dive into something pretty mind-bending today, something I think you'll find particularly interesting as a philosopher. We're going to be tackling automated reasoning.
Absolutely. It really gets at, the core of philosophical inquiry, logic, and reasoning. But instead of just thinking about, dusty old books, we're talking algorithms, computer programs.
Our guide for this journey is going to be the Stanford Encyclopedia of Philosophy's entry on automated reasoning.
Yeah.
It is dense,
Yes.
but it is packed with insights. And get this, it talks about a computer program that actually solved a 50-year-old math problem, a problem that had stumped some of the greatest logicians. It's really quite remarkable.
It really captures the essence of this field. Imagine, a problem that even baffled Tarski, a giant in the field of logic. Then this program, EQP, comes along, helps crack the code, proving a fundamental connection between Robbins algebras and Boolean algebras.
Okay, before we get into the specifics of this mathematical mystery,
Yeah.
let's just take a step back and make sure we're all on the same page. What exactly is automated reasoning? I mean, are we just teaching computers to think? Or is there something more to it?
Yeah, it's definitely more nuanced than that. So automated reasoning is really about creating systems that can perform valid deductive reasoning.
Okay.
Much like the rigorous logic used in philosophy, it's like, how do we formalize those thought processes that we use to draw conclusions from a set of premises?
So it's not about, just mimicking human thought. It's about capturing that essence of logical deduction, but in a way that computers can understand and execute. And that involves, defining the problem precisely, choosing a language to represent that information,
Yeah.
and then giving the system, a set of rules, a mechanism to make those logical leaps.
Exactly. It's about, providing that framework for logical reasoning, a set of instructions that'll guide the computer towards a valid conclusion. And of course, this has to be done efficiently.
Right?
Otherwise, we'd be waiting forever for an answer.
Which brings us back to that fascinating story about the Robbins algebra problem. It was unsolved for decades, and then boom, EQP contributes to the solution. I'm really curious to hear more about this.
So Robbins algebras are very closely related to Boolean algebras,
Okay.
which are fundamental to both logic and computer science. And the problem was to prove that a specific equation, Huntington's equation, could be derived from the axioms defining Robbins algebras. And it turns out that determining whether a set of equations defines a Boolean algebra is actually undecidable in the general case.
Undecidable. So even with all our logical tools, there are some problems that are just inherently beyond our reach. It's a little humbling, isn't it?
It is. But that's what makes EQP's contribution so significant. It couldn't solve the problem outright, but it provided a key insight. It showed that all Robbins algebras possess a particular property. And armed with that knowledge, EQP was able to automatically complete the proof, showing that Robbins algebras with that property are indeed Boolean.
So it wasn't about, replacing human ingenuity. It was about augmenting it, providing a new perspective, a new tool to tackle this problem that had stumped us for so long.
Exactly. And this is what makes me so excited about the potential of automated reasoning for philosophical inquiry. Imagine if we could, test the logical consistency of complex philosophical arguments, or explore new axiomatic systems, even potentially uncover new insights that we might have missed otherwise.
Now we're talking. This is starting to sound less like, a computer science lecture and more like a philosopher's playground. But we've only scratched the surface here. These programs rely on specific methods, different calculi, you could say, to perform this deductive reasoning. It's like they have different schools of thought, right?
That's a great way to put it. There's a whole family of these deduction calculi, each with its own, strengths and weaknesses, its own way of approaching logical inference. And of course, which one you choose depends very much on the problem that you're trying to solve.
It's not one size fits all. It's about using the right tool for the job. So what are some examples of these different calculi? Can you give us a quick tour of the landscape?
Absolutely. So first order logic is very common, very powerful for general reasoning, even program verification. Then there are modal logics and temporal logics. These are particularly useful when you're dealing with systems that involve, things like time or possibility, necessity, all very relevant to philosophy.
Yeah, I'm starting to see the connections here.
Yeah.
But no matter what calculus you choose, There are some ground rules, right? I mean, these systems can't just, spit out any old conclusion. They have to be sound and complete. Otherwise, we're just generating logical gibberish.
You're exactly right. So soundness and completeness are, fundamental in this field. Soundness guarantees that the inferences made by the system are actually valid, that if the system proves something, it must be true based on the assumptions that we've given it. Completeness, on the other hand, means that the system can actually prove all the true statements that logically follow from those assumptions.
So soundness is making sure that we're not being led astray,
Yeah.
and completeness is making sure that we're not missing any crucial truths. Makes sense. But what if a system isn't complete? Does that automatically render it useless?
Not necessarily. Incompleteness just means that there might be some truths that the system can't prove. It's a limitation, yes, but not a fatal flaw. Unsoundness, on the other hand, that's a much bigger problem. That means that the system can derive false conclusions even from true premises, and that's something we definitely want to avoid.
Right, a system that can't prove everything might still be valuable, but a system that proves falsehoods, that's downright dangerous. So we have these different calculi, we have these principles of soundness and completeness. But how do these programs actually go about constructing proofs? How do they navigate this logical maze to reach a valid conclusion?
So that's where things get even more interesting. And one very common method is called resolution. And it's based on this idea of, the chain rule of logic, like modus ponens. It works by, systematically combining clauses to deduce new information. The ultimate goal is to derive a contradiction,
Right.
showing that, the original assumptions, along with the negation of the conclusion, are inconsistent.
So if you can show that, assuming the conclusion is false leads to a contradiction, then the conclusion itself must be true. It's a clever way of, you know, proving things by proving that their opposite is impossible.
Exactly. And to illustrate how this works, let's consider a simple example. Imagine you have the statements. If it's raining, then the ground is wet, and it's raining. Resolution would represent these as clauses and manipulate them to derive the ground is wet.
Okay, I think I'm starting to get the picture. But I imagine things can get pretty complex when you're dealing with more intricate arguments. Are there strategies, to make this process more efficient? I mean, we don't want these programs getting lost in, a labyrinth of logical possibilities.
Absolutely. There are various resolution strategies that can be used to help manage the search space. One common one is called subsumption.
Yeah.
And this allows you to, discard clauses that are more specific, if you have a more general clause that already covers them. Model elimination checks if a sentence is false in a model of the axioms, allowing for its discarding.
So it's about pruning that logical tree, eliminating those unnecessary branches, and homing in on, the most promising paths.
Precisely. Another crucial strategy is linear resolution. It's very attractive because it has this, very simple linear structure, which makes it very easy to implement while still guaranteeing completeness. It basically works by resolving a clause against the most recently derived clause.
So it's like building a logical chain, link by link, always connecting the newest link to the previous one. But resolution isn't the only method in the automated reasoning toolbox, is it? What other approaches do these programs use to traverse that landscape of logic?
Oh, absolutely. There's a whole range of approaches that go beyond resolution. Each one, offering a unique perspective on how to actually automate this process of reasoning.
As we're going through all these different methods, it's making me think about, how much of philosophy really relies on reasoning about abstract concepts, especially those involving like recursion. I remember, wrestling with these ideas back in my metaphysics classes. It was always quite a mental workout.
Oh, absolutely. And it's, it highlights an area where automated reasoning can be really powerful, tackling those problems involving recursion, which are often central to computer science, and proving things about programs, that can be quite tricky using the traditional sort of logic.
Yeah, recursion, that mind-bending concept where a function calls itself. I can see how that would be a challenge to handle logically. It's almost like, a snake eating its own tail.
Exactly. And that's where mathematical induction comes in. It's a really powerful technique for proving statements that hold for, like an infinite number of cases, which is perfect for dealing with recursion where you can't just, check every single case individually.
So instead of, examining every single instance, You find a way to prove it for like a base case and then show that, if it holds for any given case, it also holds for the next one.
Yeah.
It's like setting up this chain reaction of truth.
Precisely. And there have been some, really impressive successes in automating mathematical induction. So, for example, you have the Boyer-Moore theorem prover. It's been used to verify some really sophisticated theorems. It really shows that even complex inductive proofs can be, handled by machines.
Wow, that's incredible. It seems like there's almost no limit to what these systems can tackle. But I have to imagine that automating induction comes with its own set of hurdles. It can't be all, smooth sailing.
You're absolutely right. And one of the major challenges is figuring out how to apply induction in the first place. So identifying the right induction schema, the property to prove inductively, and even determining the appropriate base case, that can be quite tricky.
I can imagine that would require a lot of ingenuity, even for a computer. It's like, trying to find the right starting point and the right pattern to follow in this vast logical landscape.
Absolutely. But, there have been significant strides in developing strategies and heuristics to help guide this process. And this has led to, some powerful systems like ACL2. It's used extensively in large-scale verification projects, particularly for hardware design.
So it's like we're equipping these reasoning systems with more sophisticated tools and techniques, enabling them to navigate, more complex logical terrains. This is really exciting stuff.
It is. And this brings us to another area where automated reasoning is really, pushing the boundaries. Higher order logic. So remember we were talking about first order logic where you quantify over, individual objects. Well, higher order logic takes it a step further.
Higher order logic, is that some kind of like super-powered logic? What makes it different?
You could say that. So in higher order logic, you can actually quantify not only over objects, but also over predicates and functions themselves.
Hold on. Quantify over predicates and functions. Now that's a level of abstraction I haven't encountered before. What does that even mean practically?
So think of it this way. In first order logic, you can say things like, Socrates is a philosopher. But in higher order logic, you can express things like, there exists a property that all philosophers share. You're essentially talking about, properties of properties. It just opens up a whole new realm of expressiveness.
Wow, that's pretty mind-blowing. It's like, it's like moving from talking about, individual trees to talking about the concept of like treeness itself. It seems like a really powerful tool for tackling philosophical questions, those that delve into the nature of properties or relations or these abstract concepts.
Precisely. But, this power does come with a price. So automating higher order logic is significantly more challenging than first order logic. Unification, for example, which is that
Yeah.
process of finding substitutions that make expressions identical, that becomes much more complex. And perhaps more fundamentally, the logic itself is inherently incomplete.
Incompleteness again. So even with this increased expressive power, there are still limits to what these systems can actually prove.
Yeah.
Are we forever chasing this elusive horizon of logical completeness?
In a sense, yes, but that doesn't mean it's, a futile pursuit. There have been some very successful higher order theorem proving systems that have been developed, like TPS and HOL. They're really pushing the boundaries of what's possible in this domain.
It seems like there's this constant tension between expressive power and the feasibility of automation. The more you can express, the harder it becomes to actually create a system that can handle it efficiently.
Exactly. And that's a recurring theme in automated reasoning. Finding that sweet spot between expressiveness and practicality. That's a key challenge for researchers in this field.
Now, speaking of expanding the scope of what we can reason about, what about those non-classical logics we touched on earlier, the ones that go beyond, the traditional confines of classical logic?
That's another exciting frontier. There's a growing interest in automating non-classical logics. And this is driven by, the needs of AI and also this desire to model more nuanced, more context-sensitive forms of reasoning.
It makes sense. Classical logic is great for many things, but
Mhm.
it doesn't always capture, the full complexity of human thought, especially when you start dealing with, subjective experiences or beliefs or the inherent ambiguity of language.
Yeah.
So what are some examples of these non-classical logics that are being automated?
Well, you have modal logic, which deals with notions of necessity and possibility. And it's, really a cornerstone of philosophical analysis of knowledge, belief, time. But it also has applications in computer science, when you're reasoning about systems with multiple agents or states.
So if you're building, AI systems that need to interact with the world, they need to make decisions, they need to be able to reason about what's possible, what's necessary, what might be the case. It's like giving them, a sense of the contingencies of reality.
Precisely. And then you have other fascinating non-classical logics like intuitionistic logic, which has deep connections to, the foundations of mathematics, constructive mathematics. You even have things like paraconsistent logic, which can actually tolerate contradictions without everything falling apart.
Paraconsistent logic. That sounds almost paradoxical. How can a logical system, handle contradictions without just collapsing into, a meaningless mess?
It might seem counterintuitive, but it turns out it's actually quite useful in certain contexts. So, for instance, if you're dealing with, inconsistent information from multiple sources, a paraconsistent logic can actually allow you to reason with that information without, everything imploding.
That's fascinating. It's like a logic designed for the real world,
Yeah.
where inconsistencies and contradictions are often just, unavoidable. It really highlights the diversity, the richness of the world of logic.
It certainly does. And, automating these non-classical logics, it's a significant challenge, but it's also an incredible opportunity. It opens up these, new avenues for exploring the nature of reasoning and has this potential to revolutionize fields like AI and computer science.
It's like we're opening up these whole new dimensions of logical possibility, exploring territories that were previously just uncharted.
Hmm.
But we've talked a lot about, the theory, the different methods. What about the practical applications? Where is automated reasoning actually making, a tangible difference in the world?
Oh, that's where things get really exciting. The real world impact of automated reasoning is vast. And it's growing rapidly. So from logic programming to SAT solvers, deductive computer algebra systems, the crucial field of formal verification, the applications are incredibly diverse.
Okay, slow down a second. We're philosophers here. Remember?
Yes, sir.
Give us the lay of the land. What are some of the highlights of these real world applications that would be particularly interesting to someone in our field?
Absolutely. So let's start with logic programming. And the most famous example of that is Prolog. It's a programming language that actually lets you write programs directly in logic. You specify, facts and rules, and then the system uses a theorem prover to answer queries and solve problems.
So instead of writing these detailed instructions for how to do something, you you describe the problem in logical terms, and then the system figures out how to solve it. It's like giving the computer a set of logical premises and then letting it deduce the solution.
Exactly. But as with anything, there are challenges. So, Prolog's reliance on negation as failure can lead to some tricky situations. And the control problem, ensuring that the program actually executes efficiently, that can be a real headache.
Those pesky philosophical issues always seem to creep into the practical world. I guess you can't escape the fundamental questions of logic and negation, even when you're building computer programs.
Indeed, indeed. But despite these challenges, Prolog has proven to be, incredibly valuable, especially in areas like AI and natural language processing.
Okay, what about those SAT solvers you mentioned? What's their claim to fame?
So SAT solvers, they're all about determining the satisfiability of propositional formulas. So essentially you have a formula with variables that can be either true or false, and the solver tries to find an assignment of truth values that makes the formula true.
So it's like a logic puzzle where you're trying to find the right combination of truth values to satisfy all the constraints. If I remember correctly, those problems can get like exponentially harder as you add more
Well,
variables.
you're absolutely right. SAT is actually an NP-complete problem, which means that in the worst case, finding a solution can actually take an exponential amount of time.
Yikes, exponential time. That sounds like a recipe for computational gridlock.
It can be, but the amazing thing is that researchers have actually developed incredibly clever algorithms and heuristics that allow these SAT solvers to handle real-world problems with, thousands of variables really, really efficiently.
Really, that's pretty impressive. It seems like we're constantly finding ways to overcome these computational barriers. What kind of real world problems are being tackled with these SET solvers?
Oh, a huge range. So they're used in everything from circuit design and software verification to planning and scheduling. They're even being applied in bioinformatics and cryptography.
So they're kind of like the silent workhorses of the computational world, just quietly solving these complex problems behind the scenes in a wide range of domains.
Precisely. And they're really a testament to the power of automated reasoning to tackle real-world challenges in practical and efficient ways. But, speaking of powerful tools, let's not forget about deductive computer algebra systems.
Deductive computer algebra systems. Now that's a mouthful. What are those all about? I have to admit, I'm more familiar with the dusty old volumes in the philosophy library than with these high-tech computational tools.
Well, you're probably familiar with computer algebra systems, things like Mathematica or Maple. They're incredibly powerful for symbolic computation.
Yeah.
So, you can manipulate and solve equations, perform calculus, explore all sorts of, mathematical structures.
Yes, I've dabbled with those systems before. They're quite impressive. But what makes them deductive? How does that tie into automated reasoning?
That's a great question. So the idea is to combine the symbolic computation capabilities of computer algebra systems with the rigor and the logical foundations of automated deduction. And this leads to what's called deductive computer algebra, or DCA for short.
So it's like taking, the computational power of these systems and adding a layer of logical certainty on top of it. Ensuring that the results are not just, fast, but also demonstrably correct.
Exactly. It's about bringing together the best of both worlds. So, the computational efficiency of computer algebra systems and the logical guarantees of automated deduction.
So what are the advantages of combining these approaches? Does it just provide, peace of mind, or are there more tangible benefits?
Oh, it's definitely more than just peace of mind. So, for one, it allows you to actually verify the correctness of the computations performed by these systems. So, computer algebra systems are powerful, but they don't always operate with the same level of logical rigor as automated deduction systems.
So there's a risk that they might actually produce incorrect results, even if they're very, very fast and efficient. It's like a car that can go incredibly fast but has, faulty brakes.
Exactly, and that's where automated deduction comes in. It can actually be used to prove that the steps taken by the computer algebra system are logically sound, ensuring that the results are actually trustworthy.
That makes sense. It's like having, a logical watchdog overseeing the computations, making sure that everything is done according to the rules.
Precisely. And another benefit of DCA is that it allows you to actually extend the capabilities of these computer algebra systems. So
Yeah.
you can incorporate, new logical rules, new reasoning
So
techniques.
it's not just about verification, it's about enhancement. You're taking these already powerful tools and making them even more versatile and capable.
Exactly. And this has led to some, really remarkable results. Systems that can actually automatically prove non-trivial theorems from real analysis or find closed-form solutions for complex summations.
It's amazing to see how these different areas of computer science and logic are coming together to create something that's truly new and powerful. It's like this synergy of disciplines, each one contributing its own unique strengths to create something that's greater than the sum of its parts.
You put it perfectly. And we've really only just begun to explore the practical applications of automated reasoning. There's still so much more to discover and explore.
So welcome back to the final part of our deep dive into automated reasoning. We've covered a lot of ground, from different uh, logical calculi to some fascinating real world applications. But there's one area that I'm particularly eager to explore: formal verification.
Yeah, it's a crucial area, especially given our, increasing reliance on these complex hardware and software systems. So, formal verification uses automated reasoning to mathematically prove that these systems behave exactly as intended, which helps to, prevent those pesky errors and ensure safety and reliability.
So it's about taking the rigor of logical proof and applying it to the design and the implementation of real world systems.
Yeah.
It's like taking the principles that we've been talking about and actually, putting them into action to build a world that we can trust.
That's a great way to put it. And, it's becoming increasingly important as these systems become more and more complex, more interconnected. You think about it, our lives really depend on the correct functioning of everything from aircraft control systems to medical devices to the software that's running our power grids.
Yeah, it's a bit unsettling when you when you put it that way.
Yeah.
But it also really highlights, the importance of getting it right.
Yeah.
So how does formal verification actually work in practice? Where do you even begin when you're dealing with something as intricate as a microprocessor or a piece of software?
It all starts with a formal specification of the system's desired behavior.
Mhm.
And this specification is kind of like a blueprint. It outlines exactly what the system is supposed to do under various conditions. And, this is often written using mathematical logic to ensure, that precision and that clarity.
So you're essentially creating like a logical representation of the system's ideal behavior, kind of a gold standard against which you can compare the actual implementation.
Exactly. And once you have that specification, you can actually use these automated reasoning tools to compare it to the system's design, the system's implementation, meticulously checking for any inconsistencies, any potential errors.
It's like having this team of tireless logic inspectors just examining every nook and cranny of the system to make sure it adheres to that blueprint.
That's a great analogy. And, the techniques used in formal verification, they're really the same ones that we've been talking about throughout this deep dive. So resolution, model checking, induction, even higher order logic, they all play a role.
So it's like we're bringing all of these tools together to build systems that are not only, functional,
Yeah.
but also demonstrably correct.
Precisely. And, this approach has had a significant impact on a wide range of fields. So one prominent example is in hardware design, particularly in microprocessor verification. So companies like Intel or AMD, they use formal verification extensively to ensure the correctness of their chip designs.
Yeah, that makes sense. Given the complexity of modern microprocessors, it seems like an ideal application for formal verification. It's like catching those subtle errors before they have a chance to wreak havoc in the real world.
Exactly. And, it's not just about, preventing these bugs. Formal verification can also be used to optimize designs. So you can prove that, certain components can be simplified or even eliminated without affecting the overall functionality.
So it's like a logical spring cleaning,
Yeah.
streamlining the system, making it more efficient, but without sacrificing correctness.
That's a great way to think about it. And, the applications of formal verification, they extend far beyond hardware. So it's also used extensively in software development, particularly for safety critical systems, where errors can have these really serious consequences.
You're right. When you're dealing with software that controls, aircraft or medical devices or nuclear power plants, the stakes are incredibly high.
Hmm.
Formal verification provides a level of assurance that, traditional testing methods just can't match.
Absolutely. And as software becomes increasingly complex, increasingly interconnected, the importance of formal verification is only going to continue to grow. It's really an essential tool for building a future where we can actually trust those systems that underpin our lives.
This whole deep dive has been such an incredible journey. It's clear that automated reasoning is not just, this theoretical pursuit. It has profound practical implications for how we design, how we build, how we interact with the world around us.
Yeah, I'm glad you found it valuable. And, as philosophers, we're really in this unique position to explore the deeper implications of these technologies. So, what does it mean for our understanding of knowledge, of truth, of the nature of proof itself when machines can perform these complex reasoning tasks?
That's a fascinating question. It really challenges us to think about the relationship between human reasoning and machine reasoning.
Mm.
If a computer can prove a philosophical argument, does that make the argument more convincing to us or less convincing? These are
Yeah.
questions that that philosophers are going to be grappling with for years to come.
Indeed, indeed. And that's what makes this field so exciting. It's not just about building better tools. It's about, expanding our understanding of what it means to reason, to know, to be.
Well said. I think our listeners are walking away from this deep dive with a newfound appreciation for the power and the potential of automated reasoning and maybe even a few new philosophical questions to ponder.
It's been a pleasure exploring this fascinating field with you. And until next time, keep questioning, keep exploring, keep pushing those boundaries of human knowledge.
And to our listeners, thanks for joining us on the deep dive. We'll see you next time for another deep dive into a topic that's sure to challenge your assumptions and expand your horizons.